Hi everyone, I'm Prerna and I'll be presenting our work, Hand Gesture Recognition for Blind Users by Tracking 3D Gesture Trajectory. This work has been done in collaboration with my advisors from Stony Brook University. Hand gestures provide an easy and intuitive way to interact with smartphones. A user can simply move their hand to trigger an action on the screen. For example, you can move your forearm right to trigger swipe right on the touchscreen. In fact, many previous works in the Kai community have built accurate techniques for recognizing the hand gestures. We asked this question: can hand gestures be used to improve the accessibility of smartphones for blind users? Traditionally, blind users interact with their phones using screen readers, which are not idle in many scenarios. Screen readers are very useful, but over the years, there has been several studies that show there are problems associated with screen readers, like they're not idle for single-handed interaction, they have overloaded gestures, and they're also susceptible to shoulder surfing attacks. Some initial work in the hand gesture recognition space has shown that blind users actually like having hand gestures as alternate ways to interact with their phones. They like that gestures provide them with the ease of one-handed interaction. They don't have to take out their phone out of their pocket. They can use screen readers anyway that read the screen out to them. In this work, we explore if we can use hand gestures using smartwatches for improving the smartphone accessibility. Towards the objective of improving accessibility of smartphone interactions, we would require two things. First one being an accurate gesture recognition algorithm that can precisely recognize the gestures of blind users. And secondly, we should be able to support a large number of gestures which can be used as alternatives to the screen reader gestures. There are several gestures that users use while interacting with the screen readers, and different users have different preferences for the gestures. We should be able to support those preferences. With the goal of accessible hand gesture recognition, we looked at some state-of-the-art works in hand gesture recognition space that specifically use the motion sensors. The initial results point that these techniques do not really work well for blind users, as they're mostly designed keeping the sighted user population in mind. We will get back to these results later in the slides. Now, to understand why these works don't scale up for blind users, we performed a comparative experiment with 10 blind users and 16 sighted users. We asked users to perform a set of 15 hand gestures across three categories, namely forearm gestures, compound gestures, and shape-related gestures. We look at gesture-specific features to compare the gestures of blind and sighted users in detail. We look at properties like variation among the users, jerk, jitter, velocity, and pause duration in the gestures. I will talk about the highlighted properties in the subsequent slides. For the other properties, please refer to our paper. The first property we look at is the variance in the gestures among the users. If we look at the motion data of two blind users performing the same gesture, that is the gesture sequences in red, they look very different. But now, if we look at the same gesture being performed by two sighted users, which is in blue, they look relatively closer. In fact, we use a template and compared each sighted users and blind users gesture with a template. On average, we see that there is more inter-user variance in the gestures of blind users than sighted users, as they lack visual feedback while doing the gestures. The high variance in the gestures among the users can potentially be solved by having lots and lots of training data from different users. But training data is limited with the blind user population, and collecting this training data is very expensive. The next takeaway from our comparative experiment is that blind user gestures have more jerk than sighted user gestures. Jerk measures the changes in the acceleration of the signal with respect to time. A high jerk means more sudden changes in the acceleration, thus more noise in the accelerometer data. Most of the motion sensor based gesture recognition works using IMUs use a combination of accelerometer and gyroscope sensor. But high noise in blind users' accelerometer sensor makes it less reliable and should be avoided. We see that similar noise does not exist for gyroscope data for blind users. We have more details on this in our paper. We also saw that blind users take longer extended pauses while completing a gesture as compared to sighted users. These pauses make the gestures more subtle and can be missed by most of the existing gesture recognition algorithms. Based on the comparative experiment, we distilled some design goals. Firstly, since the training data is limited with the blind user population, algorithms should be designed to work with less data, but at the same time, they should be able to capture high variance in the user's gestures. Secondly, the algorithms should avoid the noisy accelerometer data and should rely more on the gyroscope data for blind users. And lastly, the algorithm should be able to capture the subtle gestures of blind users and not mistake them as noise. From our study, we now know that there is high variation in the gestures of blind users among the users. Now, how can we recognize the gestures despite high variance and limited training data to learn from? So, if we look at the complete time series data of two blind users performing a forearm up gesture, it looks very different. But let's now focus on a smaller part of this gesture. This small micro movement looks similar across the two users, and we call this similar micro movement or the invariant part the nucleus of the gesture. Our previous work, Accessware, has looked at small micro movements for simple gestures and found them to be consistent for a gesture across blind users. Template matching techniques can be now used for comparing a predefined template and this nucleus to detect the gesture. We now see if we can extend this concept of invariant micro movement for more complex gestures like shape gestures and compound gestures. Let's look at two blind users performing a square gesture. The micro movement does not look similar for this gesture across the two users. The challenge is complex gestures do not show invariance in micro movement, at least in the 2D time series representation of the signal. So, we do not see any similarity in the 2D representation of free-form gestures. How about we look at these complex gestures in 3D? If we look at the 3D trajectory of two blind users performing the same square gesture, they now look similar in shape. We refer this as the approximate nucleus. It is possible that 3D representation of the gesture can help us identify durations when the gestures are similar across different users. The problem is that free-form gestures are performed in different planes and orientation. This problem renders simple template matching algorithms not a good choice to recognize the 3D gestures, as they don't take into consideration the planar and the orientation aspect of the gestures. Let's revisit. We have the following two challenges as of now. First one being, gestures in free space are performed in different planes and orientations. And second one being that there is high variance in the gestures of blind users, but very less training samples to learn this high variance. Towards this, we have two insights. The first one is, we use a combination of geometric features and look at the 3D gestures from multiple views to incorporate planar and orientation aspect of the gesture. Secondly, to overcome the lack of limited training data, we tend to rely more on pre-trained models. Let's deep dive more in the first insight. We look at geometric properties of a gesture that are invariant to the plane and orientation in which the gesture was done. Recall that even though gestures in 3D representation look similar in shape, they are not in the same plane and are in different orientations. Curvature can be one such property which is invariant, and it can be thought as measure of how bent the trajectory is at a specific point. The first figure shows curvature of a square gesture, and the 4 peaks in the plot denote the 4 bends while performing the square gesture. Another such property is centroid distance function. It measures how far from a specific point on the trajectory is the centroid from. We also look at other shape descriptors like torsion. Refer to our paper for more details on these properties. Besides using geometric features for 3D gestures, we also look at 3D gestures from different angles to take into account the different planes and orientation of the gesture. In computer vision, to identify 3D objects, concept of multi-view has been well studied. Taking inspiration from them, we look at the 3D gesture trajectories from multiple views. The figure shows a square gesture trajectory of a user from 6 different angles. Now, these gesture trajectories resemble 2D hand-drawn images. So we cast the gesture classification problem to an image classification problem looking at the images from multiple angles. We use a multi-view CNN to classify these images. Multi-view CNN image models require large amounts of training data, but this training data is not available for blind user population. Instead, we use pre-trained efficient CNN model which is trained to classify hand-drawn images. We modify the top layers and fine-tune the model to classify blind users' gesture trajectories. Now, putting everything together, we have a pre-processing block which takes the gyroscope signal of the gesture. We get the approximate nucleus boundaries and then convert this 2D representation to a 3D trajectory representation. To account for different planes and orientations in the 3D representation, we look at the trajectory from different views and also extract some plane and orientation invariant features. To classify gestures with limited training data, we use a pre-trained image classifier and fine-tune it to learn the multi-view trajectories. We use 1D convolution layers to learn the geometric properties parallelly. Lastly, we combine the two pipelines and predict the gesture. To evaluate our system, we conducted a real-world user study with 10 blind users, where we asked them to perform 15 hand gestures 10 times. Our system is 92% accurate in recognizing the gestures of blind users. We also find that using only 3 samples of a gesture from a new user, our system can achieve over 90% accuracy. This implies that with less than 1 minute of training data from a new user, our model can recognize gestures with high accuracy. When compared against state-of-the-art gesture recognition works, we achieve a higher accuracy for blind user gestures. To summarize, we characterized the gestures of blind users and sighted users and found that gestures of blind users are different from sighted users, especially for the properties like inter-user variance, jitter, jerk, pause duration, and velocity. We developed an algorithm to accurately recognize the blind user's gestures by extracting micro movements and used concepts from 3D representation of the gestures. And lastly, our gesture recognition algorithm achieves an accuracy of 92% without extensive training data using commodity smartwatches. Thank you.